This is a video walkthrough for practice 11.3. In 1 through 8, we're asked to determine if each series converges or diverges and justify the answer, and then find the sum of the series if appropriate. And we'll only find the sum when the series converges. Number 1 is a geometric series. Since each term in the series is produced by multiplying the previous term by negative 1/10. In order to find the common ratio, we can divide any term by its previous term, and negative 1/2 divided by 5, for instance, is negative 1/10. The same will be true about any term divided by its immediate preceding term. Since we know the series is geometric, we know that it may converge depending upon the value of r. We found the value of r, which is negative 1/10, which is a number between negative 1 and 1, so this series converges. Furthermore, if the series converges, then it converges to a sum of the first term divided by 1 minus the ratio. And our first term is 5, and the ratio is negative 1/10, so 5 divided by 11/10 is 50/11. In number 2, we also have a geometric series because each term can be found by multiplying the previous term by 3/2. We can find the common ratio by dividing any term by its previous term. So the second term, 3, divided by the first term, 2, is 3/2. Since the series is geometric, it might converge depending upon the value of r. Since the value of r is equal to 3/2, which is a number not between negative 1 and 1, this series diverges. Since we have a divergent series, it does not have a finite sum, so we will not find the sum. In number 3, we have a geometric series, since any term can be found by multiplying the previous term by 1/3. The ratio can be found by dividing any term by its previous term. So the second term, 9, divided by the first term, 27, is equal to 1/3. Since the series is geometric, it might converge. Since the value of r for this series is 1/3, which is a number between negative 1 and 1, this series converges. Since the series converges, we can find its sum by dividing the first term by 1 minus the ratio. The first term of this series is 27, and the ratio is 1/3. So the sum is 27 divided by 2/3, which is 81/2. The series in number 4 is an arithmetic series, since any term can be found by adding negative 1 to the previous term. An arithmetic series will always diverge, so we'll just conclude that it diverges, and since it has no finite sum, we will not attempt to find the sum. Number 5 is a geometric series, since any term can be found by multiplying the previous term by negative 3/5. The ratio can be found by dividing any term by its previous term, so the second term, negative 12/5, divided by the first term, 4, is equal to negative 3/5, the common ratio. Since the series is geometric, it might converge, and since the value of r we found, negative 3/5, is a number that's between negative 1 and 1, the series converges. The sum of a convergent geometric series is the first term divided by 1 minus the ratio, and our first term is 4, and the ratio is negative 3/5. So that gives us the sum of 4 divided by 8/5, or 20/8, which can reduce to 5/2. The series in number 6 is a geometric series, since each term in the series can be found by multiplying the previous term by negative 1. The ratio can be found by dividing any term by its immediate previous term, so the second term, negative 2, divided by the first term, positive 2, is equal to the common ratio of negative 1. Since the series is geometric, it might converge, but the value of r for this series is negative 1, which is not strictly between negative 1 and 1. So this series diverges, and When we have a divergent series, it has no finite sum, so we will not find the sum. The series in number 7 is an arithmetic series, since each term can be found by adding 3 to the previous term. Since this series is arithmetic, we know that it diverges. A divergent series has no finite sum, so we will not find the sum. The series in number 8 is a geometric series. The common ratio for the series is 2/3, since we can multiply each term by 2/3 to get the next term in the series. The ratio can be found by dividing any term by its immediate previous term. So the second term 1/3 divided by the first term 1/2 is 2/3. Since the series is geometric, it might converge depending upon the value of r. The value of r that we found is 2/3, which is a number that falls in between -1 and 1. So this series converges. The sum of a convergent series is a finite number that we can find using the sum formula for a geometric series. The sum is equal to the first term divided by 1 minus the ratio, and the first term is 1/2, and the ratio 2/3. So that gives us a sum of 1/2 divided by 1/3, which is 3/2. In 9 through 12, we're asked to write each repeating decimal as an infinite geometric series, and then use the sum formula to write in the form of a rational number or the ratio of integers. The decimal 0.7 repeating can be expressed as 0.7 plus 0.07 plus 0.007, etc., which is a geometric series with a ratio r equal to 0.1. Since the ratio is a number between -1 and 1, the sum can be found using the sum formula for an infinite geometric series, the first term divided by 1 minus the ratio. The first term is 0.7 and the ratio 0.1, so that gives us 0.7 divided by 0.9. To express this as a ratio of integers, we can multiply the fraction by 10/10, giving us a result of 7/9. In number 10, we have a repeating decimal 0.04 repeating, which can be written as a series 0.04 plus 0.004 plus 0.0004 plus etc., which is a geometric series with a ratio of 0.1. Since the ratio is 0.1, which is between -1 and 1, we can find the sum of this infinite geometric series by using the sum formula. Sum equals the first term divided by 1 minus the ratio. The first term of the series is 0.04, and the ratio is 0.1, which gives us a fractional value of 0.04 divided by 0.9. To express this as a ratio of integers, we can multiply the fraction by 100 over 100, which gives us a result of 4 over 90. 4 over 90 can be further reduced to 2/45. The decimal 0.45 repeating can be expressed as an infinite series 0.45 plus 0.0045 plus 0.000045 plus etc., which is an infinite geometric series with a common ratio equal to 0.01. Since the ratio is a value that falls in between the numbers -1 and +1, the sum can be found using the sum formula for an infinite geometric series. Sum equals the first term divided by 1 minus the ratio. The first term of this geometric series is 0.45 and the ratio 0.01. This gives us a fractional result of 0.45 divided by 0.99. We can express this as a ratio of integers by multiplying by 100 over 100, which will give us a result of 45/99. And that fractional value can be reduced to 5/11. The repeating decimal in number 12 can be expressed as an infinite series 0.021 plus 0.00021 plus 0.0000021 plus etc., which is a geometric series with common ratio 0.01. Since the ratio 0.01 is a number that falls between -1 and +1, the sum of the infinite series is the first term divided by 1 minus the ratio. And our first term is 0.021, and the ratio 0.01, which gives us a ratio of 0.021 divided by 0.99. In order to express this as a ratio of integers, we can multiply the fraction by 1000 over 1000, which gives us 21/990ths, and that simplifies to 7/330ths. In 13 through 18, we're asked to find the sum of each series in terms of x in simplified form, and then find the values of x for which the series has a finite sum. In other words, find the values of x for which the series converges. The series in number 13 is an infinite geometric series with a common ratio equal to the opposite of x. The series will converge whenever that ratio falls between -1 and 1, and that's an inequality that we can solve by dividing all three parts of the inequality by -1. Remember that that reverses the direction of the inequality, and if we want to write that inequality in standard form, -1 is less than x is less than +1. The sum of an infinite convergent geometric series is equal to the first term divided by 1 minus the ratio, and our first term is x squared, and the ratio is the opposite of x. So the sum of this infinite series is x squared divided by 1 plus x whenever x is a number that falls between -1 and +1. The series in number 14 is a geometric series with a value of r equal to x divided by 4. The series will converge if that ratio falls between -1 and +1, and so we can solve this inequality by multiplying all three parts of the inequality by 4, which gives us x between -4 and +4. The sum of a convergent geometric series is equal to the first term divided by 1 minus the common ratio, and our first term of this series is 1, and the common ratio x divided by 4. To simplify this complex fraction, we can multiply it by +4 over 4, which gives us a result of 4 divided by 4 minus x, and the sum of that series is 4 divided by 4 minus x whenever x is a value that falls in between 4 and -4. The series in number 15 is an infinite geometric series with a ratio equal to x plus 1, and an infinite geometric series converges if its ratio falls between -1 and +1. We can solve this inequality by subtracting 1 from all three parts of the inequality, which gives us values of x between -2 and 0. The sum of a convergent geometric series is equal to the first term divided by 1 minus the ratio, and the first term is 1, and the ratio is x plus 1. It's important to use parentheses around the ratio since the ratio has more than one term. So, simplifying, the new denominator turns into 1 minus x minus 1, and so this fraction simplifies to -1 over x, and that is the sum of the series for any x values that fall between -2 and 0. The series in number 16 is a geometric series with a common ratio of -3x. And the series converges if that ratio, -3x, falls between -1 and +1. We can solve this inequality by dividing all parts of the inequality by -3, which reverses the sense of the inequality, and when we put this in a standard order, it gives us x is a number between -1/3 and +1/3. The sum of this infinite geometric series is equal to the first term divided by 1 minus the ratio if it converges, and the first term is x, and the common ratio is negative 3x, so when we subtract negative 3x, we get positive 3x. So the sum of this infinite geometric series is x divided by 1 plus 3x for x values that fall between negative 1/3 and positive 1/3. The series in number 17 is an infinite geometric series with the ratio x minus 4 and converges if that ratio x minus 4 falls between negative 1 and positive 1. By adding 4 to all three parts of the ratio, we get that x falls between 3 and 5. The sum of a convergent infinite geometric series is the first term divided by 1 minus the ratio, and the first term of this series is x minus 4, and the ratio is also x minus 4. It's important when subtracting a binomial that we use parentheses. This will simplify to x minus 4 divided by 1 minus x plus 4, or a sum of x minus 4 divided by 5 minus x, which will be the sum for any x values that fall between 3 and 5. And the series in number 18 is an infinite geometric series with a common ratio equal to x minus 1 over 2. And the series will converge if if that common ratio x minus 1 over 2 falls between negative 1 and positive 1. Multiplying both sides, or all three parts of this inequality, by 2, we get negative 2 is less than x minus 1, which is less than 2. Adding 1, negative 1 is less than x is less than 3. The sum of this infinite geometric series is the first term divided by 1 minus the ratio if the series is convergent, and our first term is 1/2, and the ratio is x minus 1 divided by 2. In order to simplify this complex fraction, we can multiply the fraction by 2 over 2, which gives us the result of 1 divided by 2 minus the quantity x minus 1. Simplifying the denominator, we get 1 divided by 2 minus x plus 1. And further simplifying, that's 1 over 3 minus x. And that is the sum of this series for any x values that fall between negative 1 and positive 3.